Okay, previously we were talking about how we can use mathematical functions to represent physical signals. Particularly last time we saw how we can calculate the energy, the total energy in a signal, given its mathematical representation, x of t or x of n, and how we can calculate the average power averaged over all time. In this video, we're going to talk about certain time transformations, how we can distort the signal, or systems that distort the signal, in particular by transforming the independent variable, which for us is time. So I have a demonstration here for you that only requires your ears. So here is an original signal, 3, 2, 1.
Welcome to engineering.
Let me try that again. 3, 2, 1.
Welcome to engineering.
1 second. Okay, let's try that again. 3, 2, 1.
Welcome to Engineering 383, Signals and Systems.
Okay, so now I'm going to play that same signal, but with a time transformation. You tell me what the transformation is. 3, 2, 1. That transformation, of course, is time reversal. So we're going to talk about that today. Here's the original signal again. 3, 2, 1.
Welcome to Engineering 383, Signals and Systems.
And here's another transformation. 3, 2, 1.
Welcome to Engineering 383, Signals and Systems.
So that transformation was actually a delay. It took longer for the signal to start. Here's another transformation.
Welcome to Engineering 383, Signals and Systems.
This is signal compression. We've compressed the time, and consequently, you hear higher frequencies, actually. And then here is another time transformation.
Welcome to Engineering 383, Signals and Systems.
That's a time expansion. And so we've stretched it in time, and consequently, the frequencies have gotten much lower. So we're going to talk about all of these things today. So first of all, let's recall what you might know from high school algebra. And let's say we have a certain function. I'm going to call it f for function, f of t. Even though in our course we're going to use x a lot, x of t or g of t. But let's say our function is t squared plus 2t plus 1. Okay, and you should know that that's a parabola that opens upward versus t. So that would look something like this. Okay, that's f of t. I'm going to label that right here in black. Now, suppose we wanted to shift that plot to the right, and we'll say by 1 unit. What we could do is replace all of the t's with t minus 1. And we're going to call that f of t minus 1. So if I do that, I would have t minus 1 squared plus 2 times t minus 1 plus 1. So I'm not going to explain why that is. I assume you've seen that in high school, but this is a time translation. So we have, if we were to plot it, we would have something like this, translation in the independent variable. So if our independent variable is time, which it usually is, then we would also call this a delay of 1 unit. This is a delay of 1 unit. If I wanted to shift the original plot, the black plot, to the left by 1 unit, then what I can do is replace all of the t's by t plus 1, turns out. So this would give me t plus 1 squared plus 2t plus 1 plus 1, like that. And I could factor or FOIL this out and combine like terms and so forth and make this look a little nicer, but what I would get is something that looks like this. So this would be f of t plus 1. So we're not saying it's f times t plus 1, we're saying f of t plus 1, namely that we are replacing the independent variable t with t plus 1. And so if our independent variable is time, then what we're doing here is advancing the black signal to the left by 1. We're advancing it, time advancement. And there's nothing in particularly special about a unit of 1, and we would say in general that a time shift occurs when we take our signal. Now I'm going to just call it x of t, because x is usually what we use in this course. And maybe I have a system that shifts the signal in time, and so what we would get out is x of t minus t0. X of t minus t0, where t0 is any constant, and in the red t0 was 1, and in the blue t0 was -1. So what we can conclude is that if t0 is larger than 0, then we have a delay. And if t0 is less than 0, then we have advancement. Okay, t0 can be any number. It doesn't even have to be an integer. It can be, we can delay by half a unit or pi units or something like this. Okay, so that's the time shift. Now, and we'll go back to our original parabola. Okay, so there's our f of t, and remember this is f of t equals, we're using the example t squared plus 2t plus 1. And another thing I can do in time is replace t by some alpha t, where alpha is not 0. And if I do that, then I would have alpha t squared. Oh, excuse me. I'm replacing t with alpha t, so this would be alpha t squared plus 2 times alpha t plus 1. And what that does is that's scaling the time. And so we might see something like this. If alpha is larger than 1, if the magnitude is larger than 1, then what happens is we actually compress the signal by a factor of alpha. And if alpha is less, or the magnitude is less than 1, then we would expand like this, the signal in time. So you heard these two at the beginning of the video, expansion and compression. So such a signal or such a system would be like this, where we have x of t coming in, and then we have x of alpha t, where we scale time. So this is called time scale. Okay, so that's kind of our second of 3 transformations. And another thing I can do, I'm going to put an axis here now. This is t. And let's say our parabola, our original parabola, is over here somewhere. This is x of t. I guess we've been calling it f of t just to relate it to mathematics. But what I can do here is replace t with minus t. And if I replace the independent variable with minus t, what I get is a reflection over the vertical axis. Reflection. So this is a time reversal. Time reversal. Okay, and again, this is not f times minus t. This is replacing every t with a minus t. So if our function was this original one, right, then f of minus t would be minus t squared plus 2 times minus t plus 1. And what this would do, again, this would reflect it over the vertical axis. And a time reversal system then could be represented like this, where now I'm going to change it to x. X of t comes in, and a time reversal system would be such that x of minus t comes out like that. Okay, and then actually going back to the time scale, I didn't write it down, but we said it. If the magnitude of alpha is larger than 1, then this is a time compression. And if the magnitude of alpha is less than 1, then this is time expansion. Okay, so these are 3 of the most common types of time transformations that we can have: time shifting, time scaling, and time reversing. And I played an example of each one at the beginning of this video. Now that is continuous time. Let's talk about discrete time now. Again, feel free to pause these videos as we go. We have to be careful with discrete time, and you'll see why in a second. But let's talk about time shifting, time shift in discrete time now. So again, if I have x of n as an input to my time shifting system, then what I would get out is xn minus n0. Okay, n0 here is playing the role of t0 for continuous time. If n0 is greater than 0, then we have a delay. Our system delays by n0. If n0 is less than 0, then we have an advancement, time advance. Right? Our system would advance the signal in time. And the caveat here, though, the thing we have to be careful about is n0 must be an integer. So this is where discrete time and continuous time differ. In continuous time, that t0 could be anything. In discrete time, that's not true. It makes no sense if we were to shift our sequence, our discrete sequence, by something other than an integer. You can't shift it by 1.5 or pi or anything like that. Because remember, those indices have to be integer valued. Now, time reversal. Time reversal, a system that time reverses is similar to continuous time, where we would have xn come in and x of minus n come out. So that's a time reversal system. Time scaling is a tricky one in discrete time. So let's first consider this system here. When xn comes in, and what we get out is x of, we'll say mn, where m is a positive integer. Okay, let's consider what happens in this case. I'm actually going to just give you an example of what this would look like. Let's say our signal is something like this, where here is the origin. So maybe this is a height of 2, maybe this is 0, minus 2, 1, minus 1, 2, 1, 0, -1, -2, -2. Let's say this is our signal xn. So this is time sample 0, time sample 1, time sample 2, 3, 4, 5, 6, 7, 8, 9, and so on. Okay, there's our signal. And we might be interested in, well, what's this capital M doing? Let's consider x of 2n. So we said m is a positive integer, so m is 2. 2 is certainly a positive integer. Let's investigate what x of 2n would look like. Okay, well, if I want to know what x of 2n looks like, I can plug in values of n. So let's let n equal 0. So this would say x of 0. So at n equals 0, I would have x of 0. Well, x of 0 is 2. Now let me plug in another. So we used this guy here. That's x of 0. Now let's plug in 1. We want to know what is our signal at 1. So our signal is x of 2. So x of 2 is this guy. So now at 1, because we plugged in n equals 1, we have x of 2. So notice we missed this sample here. We skipped it. And let's plug in 2 for n. So this was n equals 0, n equals 1, n equals 2. X of 4. So x of 4 is this one. So that would go down -1. Notice again, we skipped this guy now. Okay, and so what you might start getting the idea, what's happening is that we're skipping every sample. So we're only retaining the ones I've circled in red. So our signal, x of 2n, is going to look like this. Notice that's kind of like a time compression where this one now got advanced by 1 unit, right? And then this guy went this way, and this one came this way, and this one came this way. And so now we've kind of compressed the signal into this guy by a factor of 2. But in discrete time, it's tricky because there's nothing in between those samples. So what happens to this one? What happens to this one? Well, they go away in discrete time. So we only retain every other sample. And that's because capital M was 2. So we retained every 2 samples, right? This one, then the second one, then the fourth one, then the sixth one, then the 8th one. This is called downsampling. So we have half as many samples now. We've downsampled. So again, so this type of system would be downsampling. All right, and then finally, still time scaling. Still time scaling. I'm going to use that same signal there. Let's consider if we put that signal into a system that gave us an output such that we would get n over m if n equals 0 plus or minus m plus or minus 2m, etc., or 0 else. This type of system is called upsampling. Let's see what it does. Let's see what that mathematics is telling us. Okay. So I'm going to draw call this signal x sub m. Okay, I'm going to draw x sub m of n down here. So let's say I want to know what x sub m of 0 is. So I plug in 0. Well, my signal is when n equals 0. So if n equals 0, this applies. So x of 0. Okay, so x of 0 is 2. And actually, I want to show, similarly to what we did before, I want to show when we've upsampled by a factor of 2. So I'm going to let capital M here be 2. Okay, now, let's say I want to know what my upsampled signal is at 1. Well, n equals 1 is not a multiple of 2. Capital M here is 2. So now I'm going to put a 0 there. This second piece applies. I'll put a 0 there. Now I want to know what is my upsampled signal at 2. So my upsampled signal at 2 is a multiple of 2. So this top part applies. So x of 2 divided by 2. X of 2 divided by 2, so that's x of 1. X of 1 is 0, so I'm going to put that 0 here. Now I want to know, what about x of 3, or my upsampled at 3? Well, 3 is not a multiple of 2, so this second one applies, the second case. So I'm going to put a 0 there. Now let's say n equals 4. So this was 3. What about n equals 4? 4 is a multiple of 2, so the top part applies. X of 4 over 2 is 2, so that's this signal, or this sample here, this minus 2. Okay, at 5 is not a multiple of 2, so I'm going to put a 0 there. At 6, this top part applies, so this is x of 6 over 2 is 3. So that's a 1, like that. And so what the pattern here is that we're retaining every sample, except we're putting a 0 in between each sample. So now the next thing you'd find is that I'd put a 0 here, and then we would move on to this negative 1, and then we would put a 0 immediately after, and then we would move on to this 2, and then we put a 0, and then we'd get this 1, and then we'd put a 0, and we'd put a 0, that would be this sample, and then we'd put a 0 after it, and we'd get this negative 1, we'd put a 0 after it, and we'd get this minus 2. This is what our upsampled signal would look like. And so this has twice as many samples, because we've upsampled by a factor of 2. So this is kind of like time expansion for discrete time. We've taken our signal and we've our original signal, we've stretched it by putting zeros in between every sample. And we put 1 0 there because m was 2. So we put m minus 1 samples. N minus 1 zeros in between the samples. Okay. And so this is our upsampled signal. Okay, so now we've covered the time transformation. So we've done time scaling, time reversal, and time shifting in continuous time and discrete time. In the next video, we'll look at more concrete examples.